So before we begin this problem, I just want to point out two questions that may arise. The first is that when we talk about Newton's law of gravity, we can consider objects as if all of their mass is concentrated at their center of mass. Meaning we can consider the distance from the Earth to an object as being the radius of the Earth, the distance from the center of the Earth to that object. The second question that comes from that is whether the height of a person would matter because of their center of mass. And if you were trying to be super exact, then yes, it would matter. But in terms of what we're doing here, remember that the height of a person is tiny compared to the radius of the Earth, so we're not going to consider that in this problem, though that will be a consideration in later problems. In this problem, we want to find the acceleration due to gravity of an object on the surface of the Earth. We want to find little g, the value that we've been using all semester, that I've been telling you that we can find. So here again, we're going to use Newton's law of gravity, knowing that the force of gravity on an object is equal to the mass of the object times the mass of the Earth, divided by the radius of the Earth squared, the distance between them squared. But we also know that on the surface of the Earth, the acceleration due to gravity, little g, times the mass will give you the weight of the object. So if we set those two things equal to each other, you notice that the mass of the object doesn't matter, it just cancels out. And we get a value for g, based on the universal gravitational constant, the mass of the Earth, and the radius of the Earth. And so if we plug everything in, and remember here to pay attention to the units. You want to make sure that everything is in meters, kilograms, and seconds. And so we get a value of the acceleration due to gravity, little g, for Earth, of 9.799 meters per second squared. This should not be a surprising result considering we've been using 9.8 meters per second squared all semester. But now you know where that number comes from. And now you can determine that number for every other planet in the solar system.